Hello. So this is chapter 9, and we're going to start with 9.1 probability distributions and expected value. So we're going to define a couple of things before we move forward here. First, we have a random variable, which is a function that is assigned a real number to each outcome in an experiment. Then we have a probability distribution, which is a table that lists all outcomes with their probabilities. And then last one is a histogram, which is a special bar graph for continuous values. So we're talking about, for example, age, weight, height, and so on. Something that we can measure that is a continuous. Now, um, for a histogram, the bars touch each other because it is a continuous value. They have to touch. And the bars are the same width to make sure that it's easy to read. And the heights of bars are determined by the probability. Okay, so next we're going to look at an example. Give the theoretical probability distribution for the number of heads showing when two coins are tossed. So number of heads, two coins are tossed. So let x be the random variable number of heads. So first we're going to identify the sample space with both a tree diagram and organized list. And we did this already in, I can't remember which, in chapter 8, one of those lessons. So we have a tree diagram. So what we're going to have is we'll have our first toss, which can be heads or tails. Then our second toss, doesn't matter what we got on our first toss. Our second toss can be heads or tails, even if the first one was a heads. And if tails was the first one, again, we have the option of having a heads or tails. So this is the tree diagram of this sample space. Now we're gonna do the organized list here, and we're gonna do it from the tree diagram. So our first one is heads, and then our second one is heads or tails. Our first toss is if we get a tails, we can get a heads or a tails, so heads or tails. So how many do we have? We've got 4 different options. Now, these two are the same. If we don't look at the order of how the coin is tossed. Okay, so now let's look at a probability distribution. So what we're going to do with the probability distribution is we're going to make a table. So we've got our x, which is x be the random variable number of heads. So our options are 0, 1, and 2. Now, heads, the probability for 0 heads, it's this one right here. So we have one option. So that's going to be 1 out of the 4, so 1/4. For one head, we've got these two options right here. So 2 out of 4. And then for the 2 heads, we have this one here. So it's 1 out of 4. Now the 2/4 we can simplify to a half. Okay, next let's graph a histogram here. So again, we've got heads, and this one is the probability. Probability. So our options are 0, 1, and 2, and then our probabilities, we're going to do 0.1, 0.2, 0.3, 0.4, and 0.5. Okay, let's graph the 0 heads first. So we're going to I need to make sure that it's the same width. That is 1/4 is the same thing as 0.25. So it's somewhere here. That's our 0. For 1, we have 1/2. So that's going to be over here. And now trying to make sure that my bars are the same width. And again, in a histogram, they touch. And then 2 is again 1/4, so somewhere here, like this. That's a histogram of tossing 2 coins. Okay, so let's move on. Example 2, one question asked in 2016 General Social Survey had to do with daily hours of TV viewing. The following probability distribution and histogram were created from the results. So here's our hours. Probability is right here on the y-axis. And our hours is this, no, of course, our hours is the x. Sorry. And this is the probability. So this is our x value, and this is our y-axis. Okay, now we know that it's a probability distribution because all of these are between 0 and 1. Next, we're going to see what is the sum of the probabilities given. So we're just going to add all the probabilities here. Plus 600s plus 500s, which gives us a 1. So it is a probability distribution. Remember that the total needs to add up to 1. Always when it's a probability distribution. So what is the probability that a respondent spent 1 or more hours watching TV? So we have the option of calculating all these 1 through 6 hours, but we can do it a little bit simpler. So what we can do is we can take the complement of the 1 or more hours. So the probability of x is greater than or equal to 1. We can take the complement of probability of x is less than 1, which gives us only this one here, 1 minus 0.10, which gives us 0.9, so 9/10. Okay, next we're going to look at the expected value. So suppose that the random variable x can take on the n values x1, x2, x3, xn. And suppose also that the probabilities that these values occur are respectively p1, p2, p3, and 2pn. Then the expected value of the random variable is this. So we're multiplying the random variable x by the probability. So expected value allows us to find the mean, which is the average or balance point for the random variable, and allows us to determine if a game is considered fair or favors one player. Okay, let's look at this next example. So using TV viewing results given in the previous example, find the average number of hours watched as reported by those surveyed. So we're going to take this here, and we're going to multiply 0 times 0.10, 1 times 0.21 and add all of those to get the expected value. So our E of x is going to be 0 times 0.10 plus 1 times 0.21 plus 2 times 0.28 plus 3 times 0.17 plus 4 times 0.13 plus 5 times 0.06 plus 6 times 0.05. And that adds up to 2.4 hours. So that is the average number of hours watched as reported by those surveyed. Okay, next example here. Each day, Lynn and Tanisha toss a coin to see who buys coffee, $1.75 per cup. One tosses the coin while the other calls the outcome. If the person calling is correct, the other buys the coffee. If they are wrong, they have to buy the coffee. Use a T diagram to find the sample space and probabilities, then calculate the expected value for Lynn. Is this a fair way to decide who buys? Okay, what are we doing? Here's the call. So either you call heads or tails, and then it's being tossed. So it can be heads or tails on either call. So if it's called heads, we can have heads, heads, or heads and tails. If it's called tails, we can have tails and heads as a toss. So these are the two options. So now, if we look at the correct, so if the caller is correct, that means that it's 2 out of 4, which is a half, 0.5. And that's why, because these are, we've got two of the correct ones, but then, so if the toss is the same as that, sorry, that shouldn't be. So if the, let me go back. So if heads is called, and the toss is a heads, so it would be the 2 out of 4, because yeah, because we've got the two. So this is what would be tossed, the second one. That's what I'm looking at. If it is wrong, again, there's 2 out of 4 that can go wrong, which is a half, and that's 0.5 again. So now we're going to look at the expected value. Hold on a second before we look at the expected value. So I circled this wrong. That's what I was confused about. Sorry about that. So the correct ones here would be if they call heads and the toss is heads, or if they call tails and the toss is tails. These are the correct ones. Now, for the wrong one, if they call a heads and toss a tails, it's this one. And if they call tails and toss heads, it's this one. Sorry about that. I got confused myself right there. But that's how it works. So now let's look at the expected value here. So E of x, again, so if they are wrong, they have to buy the coffee and it's $1.75. So $1.75 times the probability, which is a half. And if they are correct, the other one buys, so that would be negative 175 for them, times the point half for that one, let me, so this would be the correct and that would be the wrong. Okay, so when we do this calculation, we get a 0, which means that this is a fair bet. And that's because the probabilities are the same for both being correct or wrong. Okay, so next one. Next example. A local symphony decides to raise money by raffling off 5 prizes. One pair of concert box seats worth $400. Two prices of a dinner for two worth $100 and two prices of drink vouchers for the venue worth $40. A total of 2,000 tickets are sold at $1 each. Set up a probability distribution and use it to find the expected value of winning for a person who buys one ticket in the raffle. Okay, so we're going to go ahead and again, we need to set up the probability distribution here. Um, First, we have our X, which are the expected outcomes. This one right here, expected outcomes. And then we have our probability of the X. Now, we're going to look at box seats first. So, box seats are worth $400, but you're paying $1 for each. So that means that the box seats are going to be $399 because you paid that ticket, right? Now, the chances are there's one pair. So the chances are that it's one out of the 2,000 tickets for the box seats. Okay, next we're going to look at dinner. Dinner is worth $100. Again, we're going to subtract that $1 for the ticket, which gives us $99. And then there's two of them. So two out of the 2,000 tickets sold. Okay, our third one is going to be the drink vouchers. For that, they are worth $40. So 40 minus that $1 that they bought the ticket for, so $39. And there's two of them, so it's going to be 2 over 2,000. Now, our last one is going to be nothing. So people are buying the ticket and not winning anything. So they are losing $1 each ticket. How many tickets do we have left? So there's 5 prices. So out of the 2,000, we've got 2,000 minus 5, which means that there's 1,995 tickets left. So those tickets do not get anything. So that's why they lose their dollar amount. Okay, so let's go ahead and calculate the expected value here. We're going to start with the box seats. So $399 times 1 over 2,000. And I don't have room to write all of this out, so I'm just going to go. Next one is $99, and there's 2 out of 2,000 chances. Next one is the drinks. So $39 times 2 out of 2,000. These should all be inside parentheses, or there should be a multiplication in between. Okay, next one is going to be the negative $1 and 1995 over 2,000. Now, when we do this calculation, we get 0.66, and that it's a negative. So this is on average a loss, and this is not fair. because for every ticket that you buy, you're going to lose 66 cents at least. Um, but obviously, we're raising money, and that's how raffles work, is that there's going to be winners, but then majority on average are going to be, losing the money. But obviously it's for a good cause. So, but that's how we can calculate what the expected kind of value is. Since it isn't a negative, it is a loss. Okay, next we're going to go back to that American roulette. So remember from 8.4, the wheel has 38 slots. So there's two green, 0 and 0, 0, and then we've got the numbers 1 through 36, half red and half black. One simple wager is to bet $1 on red. If the marble lands in a red spot, the player doubles his money. Find the expected winnings for this bet. On average, what does the casino expect for bets like this? Okay, so if we think about a casino, there you do want to make money. So that's kind of where we are. Okay, hold on. I can't get this correct. So wins and loses. So our X um, is going to be you earn $2 if you win, and you lose the $1 if you don't win. Probability for each of these is. So in a red slot, so remember half are red, so there's 18 red out of the 38 slots, so 18 over 38. Then if we lose that $1, it would be landing on all the others. So 38 minus 20, 38 minus 18 is 20. So 20 over 38. Okay, we are going to look at the expected value here. So $2 times 18 over 38 plus negative $1 times 20 over 38, which gives us a $1.42. Now, if we look at this, it is less than the $1 bet, right? 42 cents is less than a dollar. So what does that mean? That means that on average, a player expects to lose. So this is not fair. So the casino expects to win. Of course, it's a business, so that's why it's done this way, so that they get a profit. Okay, that's it for this lesson. Let me know if you have any questions. Bye.